Hello, everyone. I'm Varun. I'm a research associate at the Urban Big Data Center at the University of Glasgow. I normally work with a lot of transportation-related projects using big data sources such as mobile phone data, apps data like Strava, etc. So I was supposed to be there at the Tartu conference in person and speaking about this work in front of you guys, but unfortunately, me and my colleague Faraz couldn't acquire the visa due to some sort of appointment issues with the Estonian embassy. So we are very extremely disappointed that we couldn't make it there, but hopefully recording our work and sharing it with you guys at least serves the purpose of being able to present this work. Okay, so today we are going to talk about estimating OD matrices using mobile phone app data. And this is in regards to a novel approach or a new simple approach that we developed in order to address some sort of issues that come with this data when we are trying to do any kind of longitudinal comparison across different years. So the brief overview of my presentation is that I'll quickly give you an introduction, then talk about our methodology, and then later on we'll look at the results of the study. So in the introduction, we see that in order to understand human mobility better, we need better data set and better understanding will again assist in transportation mobility and infrastructure policy. And most of these transportation policies use traditional data sources such as household surveys, questionnaires, etc. These traditional household surveys or questionnaires have some limitation that they're not rich in spatiotemporal extent and can be tricky to collect and can often underreport shorter trips when it comes down to travel diary surveys. So the new forms of data sources are becoming much more popular in order to do these kind of studies. And when it comes down to transportation, there are a lot of studies that have used CDR data or GPS data in order to make some sort of mobility estimates. And these kind of data gives us new opportunities and CDR data has been used in literature quite extensively in order to determine OD matrices, whereas the app data or the GPS data from these mobile apps have not been that extensively studied. And there is an advantage of using this GPS data over CDR data because they are more precise on location compared to the CDR locations. However good these data sets are, there are some challenges that come along with them. That one of the challenges is the consistency of the data across different years. Any kind of changes in some sort of apps policies or operating system policies or privacy protection policies can change the data consistency, again making the longitudinal comparison difficult. The individual behavior can change over time, how they use the app and whether they have uninstalled the app, etc., can also skew mobility. And therefore, we are proposing one way of weighting these user activity in order to get correct information when it comes down to comparing these mobility estimate across years. And we also weight these OD matrices for social demographics like Scottish index multiple deprivation and also geographical level for council areas. Okay, so then quickly looking into methodology, we have a lot of data for major cities across UK, but for this study, we are only focusing on the Glasgow City Council region, which comprises of 8 council areas, including Glasgow City. The data we are looking at is the 3-year data from Huck.io, which we received for 2019, 2020, and 2021. If you look into the data, we have 10,000 users in 2019 producing 22.7 million GPS points, whereas in 2020, we have 30,000 users and they produced 169 million GPS points. For 2020, we have similar number of users, but it generated much more data compared to 2020. So it is 356 million now. So you can see that the company that is recording these data is also focusing on selecting users that produce more data and also select apps that record more data. So therefore, this variation in this data can create problems when you are trying to do some sort of longitudinal comparison. So the methodology in order to estimate these OD matrices using this GPS data is basically divided into 4 major steps. The first step is data cleaning. Then we move to stop node detection. Then we go to trip extraction. And finally, we weight the OD matrices. So these are the four major steps. We'll talk in details for each step. So the first step, that is data cleaning. We take the raw data and then we try to clean for GPS pings that are not that accurate. For example, the first filter is the speed filter. Wherever two consecutive GPS points show that the speed is greater than 200 kilometers per hour, we reject those GPS pings. Once we have cleaned for speed, we go for impression accuracy filter, where wherever the GPS pings accuracy is actually greater than 100 meter, we reject those GPS pings. And that's where finally we get a cleaned data set with GPS pings that are much more accurate. Once we have this clean data, then the next step is to determine stay location of these users or stop node detections. So a state would be defined whenever a device doesn't move beyond a predefined distance threshold for over a specified duration. Now, this predefined distance threshold in literature, there is no clear consensus. Some studies have used 100 meters, some studies have used 200 meter or 500 meter. Therefore, in this study, we used two commonly used values, that is 200 meter and 500 meter, and then compare their mobility estimates with some sort of traditional household surveys in order to see which threshold does better. So this is the overall procedure of stop nodes. We have this GPS point collection. We have the predefined distance threshold, either 200 or 500. If the first point in that cluster and the last point time duration is greater than 5 minutes, then that cluster would be defined as a stay location. And then we check for all of the clusters within, for all of the GPS points in this trajectory, and then define these stay locations. So in this case, the in-between stop is not a stop node because the stay duration is not greater than 5 minutes, whereas the stop node B is 1. So the trip would be from point A to point B. So this is overall how we define trips and how we detect stop nodes. So once the stop nodes are detected, we are extracting the trips. And so once we take either distance threshold 200 meter, 500 meter stop nodes, we need to see whether these consecutive stop nodes actually is a valid trip or not. So for this, we can put two conditions: that if the arrival time at the stop node and the arrival time at the second stop node, and the difference between them is greater than 60 hours, then that is not a valid trip. And similarly, if the travel time is greater than 24 hours, then again, that is marked not as valid trip. So these filters are applied so that we get certain trips that are valid. And it happens because in these kind of data source, which is coming from apps, we might get stop nodes that are that the difference is over 5, 6, 10 days, even months. So we need to correct for this. So that's the procedure of trip extraction. Once we get this clean trip data, we spatially join it with the Glasgow City Council region, and then we get the initial unweighted OD matrix. So then we come at the final step of our methodology, that is the weighting, which we are proposing a new method. Here we are suggesting that we need to weight using the activity level of these users within the data. So I'll explain that soon. But the first step is to first filter out users that are representative users. So in order to do that, we are only keeping users that are active for at least a week in that entire year, and are also producing trips per active days, which are somewhat reasonable. So if the trips per active days is greater than 0.2, we are keeping those users. And if they're active over a week, we are keeping those users. Otherwise, we are rejecting those users. So this is done to keep only representative users. So since we are going to scale them back to the population so that it doesn't skew our estimates. So once we have these representative users, we are applying the first level of weight that we are suggesting is the individual level scaling. So here we are applying a weight which is a function of how active that user was. So it's a very simple scaling factor. For example, if a user was active for 6 months and made 500 trips, so that means in a year, that person would make 1,000 trips. So it's a clear direct scaling factor based dependent on the activity of that information within of that user within that data set. And once we have applied this scaling factor, we move to individual level weighting, where we weight for different SIMD and council level weights. And this gives us unbiased estimates. And then once we get that, we finally scale it for the entire population of the Glasgow City Council region to get the annually weighted annual matrix. So this completes our entire methodology. And now let's look into the results that we get for this data. So now, if you see the initial result, these are the trend for annual trips. That means how many trips were made in each year, and we want to compare how the trend looks across year. So if you see the first facet or the first plot, we see that these are raw trips that were detected from the mobile data. And we see that the trips for 2019 is much lesser than 2020, and 2021 it increases and then drops in 2022. This is clearly wrong because we expect 2020 and 2021, which are the pandemic years, to have lesser trips compared to 2019 and 2022. And this is happening because the trips that we are extracting from this data is a function of how much data they are producing, how much active these users were, and how many apps we use. So all of these are messing up with these numbers. So we first apply the SIMD weight and the global scaling weight without applying the individual level scaling. So the trend changes, but we don't see the correct expected trend again. So in the second facet, we still don't see the corrected trend because 2019 is still lesser than 2020 and 2021. So that means just applying SIMD and global scaling will not correct the trend. But as soon as we apply the individual level scaling, when we are applying for this activity users level weight, we see that the trends become much more expected. So we get 2019, which is higher than 2020, then it further decreases in 2021, and then increases in 2022. And why it drops for 2021 compared to 2020. So we did this again, but at the quarterly level rather than annually. And here, if you see again, the raw trips and the SIMD corrected trips were not giving the correct expected trend, but the last plot gives us the correct plot or the correct trend. So here you can see that the 2019 quarter 3 and 2019 quarter 4 are quite high trips, but also 2020 quarter 1 is as high as 2019 quarter 4. This is because the lockdown didn't happen by the end of the quarter 1. So it technically started at quarter 2. So we can see that from quarter 1 to quarter 2 there is a steep drop, and that's what we want to expect, that during the lockdown people stopped traveling that much, and that's where we see the pandemic years, the trip levels are much more lower when compared to the general years, and then it comes back to normal levels when in 2022. So these results make much more sense. And next thing, we compare these results or the OD matrix that we derive from these data set with the traditional data source such as Scottish Household Survey. So here we see that for both threshold 200 meter and 500 meter, the pattern that we see compared to the Scottish Household Survey, it is quite similar, and these numbers are quite close. So the mobile data is actually doing quite well, irrespective of whatever threshold you use. So in order to compare them quantifiably, we computed this square root mean error for these OD matrices, and we see that the values for 500 meter are much smaller than 200 meters. So that means they are aligning more closely to the household surveys. We even compared these trend lines with the Google Mobility trend data set, which is a totally independent data set, in order to see whether our trends still make sense and further validate the trends. So we see that whenever there is a drop in the Google Mobility data set, which is the black line, we also see the trend dropping for our data set. When it increases, our increases. When it decreases here, it decreases. So the trends again match in the direction compared to the Google Mobility trend. However, there is one steep increase here, which we need to see why this is happening. It might be down to the differences in data sources. And finally, we compare the tripling distribution, which is coming from different thresholds compared to the Scottish Household Survey. We see that the 200-meter threshold detect far more shorter trips compared to the 500-meter threshold. And this could may be possible because of surveys tend to underestimate shorter trips, and that's why 200 meter is detecting far more shorter trips, which people might not be stating in the surveys. And therefore, if we are analyzing only short trips behavior, maybe 200 meter is better than 500 meter. But if you are trying to do it for entire general trial purpose, maybe 500-meter threshold is better than 200-meter threshold. So it totally depends on what kind of study you want to do. So finally, conclusions of the study would be that these variation in these data collection policies can complicate longitudinal comparison. Our methodology corrects for uh, these complications and gives an expected trends, and that's why waiting for activity level might be the better way to go. 500-meter threshold aligns more closely with the survey data, whereas 200-meter does better when it comes down to shorter trips. And the spatio-temporal richness of mobile app data make it a very valuable data source comparing the mobility insights. So thank you so much.